Right, so this is a bit more kind of condensed version of the talk. Well, I mean, a bit more condensed talk. It's not an hour, it's only 20 minutes, so should be better. And this is actually the work that we've sent to CDC, and the talk that you should be able to see there as well. Anyways, what we've been working on in recent time is electromobility. And why electromobility? Well, I mean, one topic that has been extremely popular in these, well, lately has been decarbonization. And there's a lot of talk about decarbonization of various sectors. Of course, the first sector that comes to mind, of course, is the power sector, the power system, where, of course, if we do not decarbonize the power system, then everything else is a bit futile. And there has been a general move towards renewables, which bring, of course, many benefits, but also bring a bunch of problems to the power system itself. Namely, well, for some of the reasons they tend to be remote. You cannot really build a wind park wherever you want. You can, or even more, you cannot build a hydro plant wherever you want. You need a river and all of that. And also they are intermittent, so you cannot really plan for when you will have these renewables available, and that is most visible with solar and with wind. So when you want to have them, a lot of times you don't have them available. So those are all things that pose problems to the general power system. On the side of the traffic, the type of decarbonization that we want to see is the gradual shift towards electric vehicles. I'm talking again about road traffic. Of course, trains are trains, but that's a different story. So we are getting a slow but seemingly irreversible transition from internal combustion engine vehicles into electric vehicles. But this is also another thing. So while it brings benefits in its own, it is likely going to cause a bunch of problems for the power system as well. And from the most simplistic influence that it will have is the charging of these vehicles will of course introduce a huge demand for electricity into the power system. However, and also this demand might happen at weird times in the day. However, this does also provide us with an opportunity to, for example, store the energy generated by these intermittent sources and in a sense patch the power system that we have and help introduce intermittent sources into the general system. So in that sense, the transportation system and the power system are becoming more and more coupled. And I did a bit of a back of the envelope calculation to just see how coupled they might get. It turns out, if you look at the 3-lane highway, you assume that around 20% of the vehicles on the highway are electric, which is quite absurd for most of the world. But for example, in Norway, that is the situation that we have today. So in some near future, maybe we'll have that somewhere else as well, or in many other places as well. If you then assume that an average battery of this electric vehicle is 40 kilowatt hours, then this turns out to be approximately equivalent to the type of power that you can transfer by a 110 kilovolt power line, which these boys that you see everywhere. So it is not a lot, of course. I mean, I'm not proposing we replace power lines by roads and electric vehicles, but it is enough that this is no longer on the scale of distribution. So this is the lower end of the transmission system. So at any rate, this is something that will have an influence on the power system overall, and we should probably be thinking about how do we look at this whole problem a bit more holistically. So the main problem of this talk is how can we describe and later, when we know what we're doing, control the interaction between the power system and the transportation system. And the answer here, the partial answer here, is what we propose as a coupled traffic energy and charging, or CTEC model. Again, I think I'm showing this like for the third time today, but yeah, so it's a different vehicle model now, though, because Apart from the vehicle, the model of the motion of the vehicle itself, what we want to add is the dynamics of the battery of this vehicle. And we assume, again, that the motion of the vehicle will depend on the local traffic conditions, and that the dynamics of the state of charge of this vehicle depends as some function of the vehicle velocity. It can also have constant terms, it can be a general function. Okay, so of course, we don't really want to deal with individual vehicles, so how do we bring this into the macroscopic realm? Well, the motion part, so that is simple, that I already talked about, that ends up being essentially LWR. Once you aggregate all of these trajectories of the vehicles, you end up with a well-known set of equations. And the harder part here is, how do you think about the state of charge? Turns out, maybe somewhat expectedly, you can model this state of charge. If you look at an aggregate of all of these vehicles, then you can model the state of charge as a quantity that is being transported by the vehicles themselves. So somewhat fittingly, you can describe it by this transport equation. And this is a non-homogeneous transport equation, or advection equation, which is linear in the sense that the speed of the advection does not depend directly on the state that we're considering. So you have the transported quantity, it is transported at the speed of the traffic, and then you have the inhomogeneous part, and then the inhomogeneous part takes care of this discharge of batteries as vehicles drive on the road. So notice that this is a coupled system, but the coupling only goes one way. So the coupling only goes from the traffic to the state of charge. We don't have necessarily a coupling from the state of charge to the traffic, because we assume that essentially we assume that vehicles never run out of battery. And in that case, yeah, they will be acting as normal. We assume that we have responsible drivers. The rest is more or less the same. And by the way, this function, this discharge function here, is of course very much related to the discharge function that we were talking about in the microscopic setting. And if all of the vehicles have the same discharge function, then it is exactly the same. Otherwise, we take some sort of an average of the behavior of the batteries of all of the vehicles that we have there. By the way, right here, we are assuming that all of the vehicles are electric. We can easily relax that assumption for now. That's just for the simplicity of presentation. I can talk about how to do that if you are interested later. So that, by the way, covers the CT and D part, so coupled traffic and energy. What about charging? So charging stations are particularly important because they're essentially the only interface that we have between the traffic and the power system. So they, in a sense, sit between. And to the traffic, a charging station can be seen just as a pair of on and off ramps. So you have an off ramp going from the road to the charging station, and then you have an on ramp, and some traffic flow re-enters the traffic, right? Now, the state of charge of this flow will, of course, be different, because vehicles, in general, vehicles with lower state of charge will be leaving, higher state of charge will be returning. Okay, that part is logical, I hope. For the power side, I should say that in this talk, I do focus heavily on the traffic side. So from the power side, this charging station should be considered in a sense as a varying demand. And also, potentially, if technology of vehicle to grid power transmission matures, then we might be able to consider it to be also storage. And that's kind of the ideal. So there are two things important about modeling charging stations. One thing is we do want to track the state of individual charging vehicles, not on vehicle-to-vehicle basis, but basically we want to avoid the situation where we have, there's one empty vehicle with empty battery in the charging station, and then there arrives a vehicle with a full battery, and now we have two vehicles with 50% battery. So that is not something that we wish to avoid. We wish to have at least some delineation according to the state of charge. And then also, we want to be able to give different vehicles different charging rates, or at least vehicles with different state of charge, different charging rates. And I will illustrate why that's good in a second. So what we end up with is something that looks very much like LWR, and it is indeed just a conservation law, but it is a very different conservation law in a couple of ways. So whereas in LWR, whereas in LWR we have something, traffic density, that evolved according to space and time, here the evolution of this state is given in the state of charge space. And what I mean by that is you can think of vehicles being charged as vehicles traveling up the state of charge kind of state. And that is kind of illustrated up here. So the independent coordinate is now not space, it is state of charge. What the conserved quantity here is essentially the quantity of vehicles that are, or rather the distribution of vehicles at different states of charge inside of the charging station. And if you sum over, or if you integrate over all state of charges, that will give you essentially the number of vehicles at the charging station at that point. The final part is the charging rate, and notice that now that we have this state of charge space, we can now define this charging rate to be dependent on the state of charge, and by doing that we can, for example, charge the emptier vehicles faster than the ones that are closer to being full. Here's an example. So here we had 5 vehicles at 20% of state of charge, 2 vehicles at 50%, and then we had some 4 vehicles that were full. So let's say we want to charge these vehicles twice as fast as these ones. So after some time, the situation will be updated to this. And by the way, the vehicles that are full stay being full. We're not charging nor discharging them. And yeah, so the updated situation looks something like this. Now, let's say the power operator says, okay, we have, the wind is no longer blowing, we need some power, can you please give us some power back? So then what we can do is we can take these vehicles that are at 100% charge, and we can actually give them a negative charging rate so that they would actually discharge some power while we are still charging these vehicles that are not full at, albeit at the lower base, at least when it comes to the one at 40%. So then the updated situation would look something like this. And notice that between here and here, we actually overall negatively charge the vehicle. So on average, the vehicles have been charged with a negative charging rate, which means that we are returning the energy from the charging station to the grid. So that's something that we can do. In this particular work, we did not do any control on that part. We didn't have enough time, but that is certainly something that we're interested in doing in the future. So the full model looks something like this. And of course, I'm a bit dishonest when I said that that's the last part. The final part, of course, are the ramp flows between the charging stations and the road. But in the interest of simplicity, I will not talk about them. The important thing about ramp flows is as long as we're ensuring that we're not losing any vehicles as they move from the road to the charging station, and we're not losing any energy as the vehicles move, but we're still fine. So, okay, we want to do some control on this model. Let's first discretize it, of course. And I mean, LWR, we know how to discretize it, we get CTM. It's a very similar situation when it comes to this conservation law, because it is very similar to LWR. The difference is the speed can now be also negative, so that changes the structure that we will end up with, but the procedure is exactly the same. So we apply a Godunov scheme, we get something that looks like a CTM, but also with potentially negative speeds.
Excuse me, K is the index for the cell or for the ramp?
K is at the time step.
Okay.
The ramp is actually this Z.
Okay.
So yacht is the So yacht is the discretization in the state of charge space. I is the discretization in space, and then the K is the time step. Okay.
Sorry.
Okay. Thank you for the question. So the ramp flows more or less, well, once we define them, more or less straightforward how to get the discretized versions. It's just discretized in time. The complicated part is the state of charge, and that is because the state of charge actually is not a conserved quantity. And you might think, okay, that's because we have some discharging, the discharge or battery discharging. Actually, even if we put the battery discharging to 0, it's not a conserved quantity in the exact term of that word. So we cannot apply a Godunov scheme on that, and we cannot discretize it in the same way. However, we can instead apply a very similar scheme to this here. So we can multiply the state of charge with the traffic density, which gives us in some sense a normalized energy density in a sense. And then that is something that we can discretize. And the way we do that is we solve the Riemann problem, or the Riemann-like problem, because now we don't have a conservation law necessarily. I mean, you get some, for simple flux functions, you get decently simple results, where you see that these circles, the color inside of the circles here indicates the state of charge. And you can see that as the vehicle goes faster, the state of charge drops faster than is the case with the vehicle that is going through congestion. The differences here are over exaggerated just to illustrate what is going on. Other than that, very similar procedure to Godunov scheme. Okay. So now that we have this model, what do we do with that? Well, we implemented a bit of a control example where a toy example, where we were looking at the ring roads. We have one charging station and one on and off ramp pair. We're acting as sort of a disturbance to the model. The actuation that we assume we have available is we assume that we can set the splitting ratio of vehicles that leave the road towards the charging station. Now, of course, we cannot force the vehicles to go charge, but perhaps we can make it really cheap for them to charge at some time and then incentivize them in these kind of ways. All right. What did we want to do? Well, we had 3 control priorities. In this case, the first control priority was to ensure that the average state of charge on the road was greater than some limit. The second priority was to minimize the maximum number of vehicles. And then the third priority is if these two are satisfied, then we wish to regulate the average state of charge into, oh no, here comes that Jerome again. Then we wish to regulate the average state of charge to some reference value. Okay. The way we do that is we implemented the cascaded control law, and where the inner control loop is basically, its job is to regulate how many vehicles are charging at the charging station, because that will, in a sense, control how much energy we're injecting into the road. That is a simple gain scheduled anti-wind-up PI control. And then the outer loop is just another, the job of this inner control loop is to make the total number of charging vehicles go to some sort of a reference value. And that reference value is provided by the outer control loop, whose job is to regulate the average state of charge on the road. And that is, again, a gain schedule, not a gain schedule, the anti-wind-up PI, a very simple control. Okay, so that does take care of the third priority. Now, for one case of control, we achieved the first 2 priorities by simply carefully tuning the parameters, so nothing very smart. But for the second case of control, what we did was actually introduce some dynamic control constraints. And the idea here is that we will ensure that the average state of charge is never below some limit by limiting the minimum number of vehicles charging, or the reference minimum numbers of vehicles charging. And then we minimize the maximum number of vehicles charging at the same time by upper bounding this the reference. So providing these dynamic constraints. And we calculate these dynamic control constraints based on the prediction model, which uses a simplified model of the entire route. Okay, in the interest of time, some results, and I'm over time already, but some results. So you can see the traffic density profile up here. Here you have the situation at the charging station. State of charge on x-axis, time is always on y-axis. Here, space is on x-axis, and here as well. Here we're showing the state of charge on the road. So, and of course, and in the end, we have our control signals up here. So you can, well, one more thing, in order to make our job, well, our job harder, we introduce a disturbance in the form of, so at first the flow from the on-ramp is constant, and then at the fourth hour, so fourth hour to fifth hour, we inject more vehicles onto the road, and also reduce, and also note that the state of charge of the vehicles that are entering the road in this case is quite significantly lower than the state of charge of the vehicles that are on the road. So it's like 20% or something. Okay, so what happens if you look, and by the way, the yeah, so I'm not sure how informative the state of charge heat map is, but some things you can notice, hopefully, if the resolution is good enough. First is once these vehicles, by the way, the dashed black lines indicate the positions of the on-ramps, on and off-ramps, and then the dashed blue lines, the positions of the charging station. So you can see here, when these low state of charge vehicles are entering, this color is a bit colder than the color otherwise, and then also downstream of the charging station, the state of charge is much higher because the vehicles have, some vehicles have just charged. Okay, so this is the case that we have if we don't have the dynamic control constraints. And by the way, looking at this normalized energy density, the situation looks like this. So maybe a bit more illustrative, I don't know. Yeah, so this is the case where we tune the parameters of PI controllers in order to achieve these first two priorities. A more involved, so to speak, control approach was involving these dynamic control constraints. And you can see the dynamic control constraints in dotted purple here. So the lower bound on that reference and the upper bound. And essentially, to cut a long story short, what is happening here is that because we have some precognition about this disturbance that is going to come, and because we have a prediction model, then we predict that it will be good, or rather, in order to avoid having the minimum of having the average speed break the minimum bound, we will essentially pump more energy in before this disturbance comes. So before the disturbance, the number of charging vehicles will be higher compared to this case. And yeah, and the control does work. So comparing them, you can see that both controls fulfill the first control priority. The one with dynamic control constraints, the one with achieves that with a significantly lower total maximum number of concurrently charging vehicles, and then they also do manage to regulate the average state of charge to the reference value after the disturbance is gone. Okay, so hope to have shown that transportation and power systems either are or for sure will be intrinsically coupled, and we will need to consider them as such, and that the state of charge can macroscopically be described by an inhomogeneous advection equation, and that by controlling the charging station, we can both affect the traffic and the state of charge. So yeah, we'll talk about more the future work in the questions part. So yeah, thank you for your attention.